Right, so now I want to walk through an example with you. It's kind of a famous dynamics problem where we have three blocks being towed and the three are connected by strings. And the question is asking us to calculate the tension force in each of the strings. And obviously in the question, we're given some information. So it's towed, or it's pulled to the right by a force of 70 newtons. That force is 70 newtons. And there's a coefficient of friction between the crates and the ground of 0.33. And find the tension in each string. So we got three strings we want to calculate the tension in. So to start off this problem, we're going to draw a free body diagram and we're going to combine all three blocks into one. And this is just for the sake of making our calculations easier from the beginning. So what we're going to do is we're going to add up our masses of the blocks. So 4 kilograms plus 3 kilograms plus 6 kilograms, that's going to give us a total mass of 13.0 kilograms. Now I'm going to draw this big mass that represents all three of our blocks in one. So it's 13.0 kilograms, and it represents all three of our blocks in one. And we just want to calculate the forces acting on this unit, this whole mass of blocks. So we know 70 newtons is what we're being pulled by. So I'm going to draw that here, 70 newtons. 70 newtons. And then the next force that we know is that there's going to be a gravitational force. It's called Fg. And we have a formula to calculate Fg, that is m times g. So mass of the object, times gravitational constant. So we just have to plug in some values here. So the masses are 13.0 kilograms. And our gravitational constant that we all have memorized is 9.81 meters per second squared. So just plugging this into our calculator, we get that Fg is equal to 127.53 newtons. And I want to put a box around that. I want to put a box around that just to keep our values differentiated from our calculations. And that is equal to 127.53 newtons. That is our Fg, the force of gravity. And another force we're going to have is the opposite of the gravity. That's the normal force. Call it Fn. And in this case, it is equal to Fg. Because these two vectors, these two forces, are in opposite directions but equal in magnitude. So our Fn is also equal to, Fn is also equal to 127.53 newtons. And I'm putting a box around all of our values here, just so they're distinguished from our calculations. And then this last one that we're going to have is the force of friction. So the force of friction is going to be what's acting in the opposite direction of the motion. So if we have a box, if we have a box that is being moved in this direction, the friction is going to pull in the opposite direction of the motion. Whereas if we had a box that was being pulled in this direction, then our friction would be in this direction. So the friction's always opposite in direction to the motion. So in this case, our friction is going towards the left. And the formula for that is mu times the normal force, which is equal to 0.33 times 127.53 newtons. So the force of friction, doing this in our calculator, we can calculate it now to be 42.08 newtons. So just like that, we have the forces for this entire system all as one object. And the reason why we're doing this is because there's one more value that we're going to need later on in the problem, and that is the acceleration of our system. We need to know, since we're being pulled with a force of 70 newtons, what is going to be the acceleration of this whole system. So to do that, we're going to use our formula. F net is equal to ma, where this a value, that's our acceleration. And to do this, we're going to be looking in just the x direction. So we're looking at these two forces here for our F net. So our F net, with positive x being this way and positive y like this, we're looking again in just the x direction where this is positive, this direction is positive. So when we're writing our F net, we have a positive 70 and a negative 42.08. So let's write these out. 70 minus 42.08, and that is equal to our MA. So M, we know, that's our mass, 13 kilograms. Then our acceleration, which is unknown. So now let's rearrange this equation. I'm going to bring this 13 kilograms over to the other side, and I'm also going to type this in my calculator and get 27.29 newtons. I'm going to write the units up here, newtons and newtons. So this, in our calculator, we get that over, and I'm bringing this 13 kilograms to the other side as a division, and that leaves us with just our acceleration. So it's equal to A. And again, all we have to do is put this in our calculator, and we're going to get a value of 2.1477 newtons per kilogram is equal to acceleration. So I'm going to write that A is equal to, and I want to round this. I'm going to round it just to 2 decimals, so 2.15. And the units, remember, are newtons per kilogram. But that's not, these aren't the units I want to leave it in. So what's a newton? Well, a newton is a kilogram meter per second squared. So I'm going to write this per second squared like this, per second squared. And then this kilogram is also going to be written on the bottom. And what do you notice now? The kilograms cancel out. So our acceleration is equal to 2.15 meters per second squared. So you can see meter per second squared, that's what we're left with after the kilograms cancel out. Oops. So although the question is not asking us for an acceleration, it is still an important value for us to find when we're solving this problem. So we're gonna keep track of this. This acceleration is an important number for us. So now let's move on to the next step. And actually, before we go on to the next step, I want you to see we already know the tension in string 1. String 1 is just 70 newtons, so we don't need to solve for that. We know the tension in string 1 is 70 newtons. So that one we got done. The next one we're going to look at is string 2. And the method that we're going to find the tension in string 2 is really similar, but we're going to just be looking at these two blocks as one unit and kind of cutting the string here. So we're going to cut off the string and this green line and look at just these two units. So let's look at that. So here we're going to be finding tension in string 2. So let's find the tension in string 2, and remember we need to add up our masses, 4 kilograms and 3 kilograms. So 4.0 kilograms plus 3.0 kilograms is equal to 7.0 kilograms. And I'm going to draw this unit here, 7.0 kilograms. And that is these two together. And just like we were doing previously, we're going to assign the forces here. So we have a force of tension. So I'm going to write it F tension. And unlike here, we don't know what this tension is. This is the value that we're trying to find. So right now it's our unknown. Now let's look at some information we do know. Fg. So the force of gravity pulling straight down is equal to mg. And we know both of these values. We know that m is 7 kilograms and g is 9.81 meters per second squared. So that means our Fg is equal to 68.67 newtons. And then likewise, our Fn, or F normal, our normal force, is equal to Fg, which is equal to 68.67 newtons. And then the last force is our friction acting in the opposite direction of the motion. So motion goes this way, friction pulls us this way. So force of friction is equal to, and our formula for that is mu times Fn. So 0.33, remember that value was given in the question. That's our coefficient of friction. Multiplied by Fn was 68.67 newtons. So that means our force of friction is equal to 22.66 newtons. All right. Again, I'm just going to put boxes around these so that our values don't get confused with our calculations. And now, remember when I was telling you about this value that we found for acceleration, how this is going to become useful later on in the problem? Well, this is exactly where we're going to use it to solve for the force of tension. So remember our formula, F net is equal to ma. Let's look at our F net. Our F net is the sum of the forces of these two. And we don't know what F tension is, what the tension force is, but we do know it's positive. It's going in this direction, so it's going to be a positive. And we do know force of friction. So let's write them out like this. F tension, because it's our unknown value, minus 22.66 newtons. So that is our net force there. And then what is our mass and our acceleration? So our mass is 7 kilograms. So 7.0 kilograms. And then the acceleration, look at this. This acceleration, we need a value for acceleration. And if we have that, then the force of tension is our only unknown. So let's go back here and take this value for acceleration of 2.15 meters per second squared. 2.15 meters per second squared. And the reason I can use this acceleration here, again, for this unit here, is because when these three boxes, they all move at the same speed with the same acceleration. So when we're pulling it, the three boxes, they're all going in the same direction, same speed, with the same acceleration. So once we find the acceleration of this big unit here, we know the acceleration of each box individually because it's going to be the exact same. So all we have to do now is isolate our unknown. So F tension is equal to, remember the other side of the equation will stay the same, except we're bringing this subtraction to the other side, and it's going to become an addition. So plus 22.66 newtons. So force of tension is equal to 15.05 newtons plus 22.66 newtons. Going one step further down, 37.71 newtons. So that tells us that our force of tension is equal to, I'm going to round this to two significant digits, 38 newtons in second string. So 38 newtons in the second string. So this force of tension here is equal to 38 newtons. That's this string here. This string here, 38 newtons. Because we're looking at these two, we looked at these two blocks as one. And then that is our tension. So all that's left to do now is find the tension in string 3. So to do this one, we're not going to be combining any boxes. We're going to look at just the last box, making our cut just right here, looking at just string 3. So let's come over here. I'm going to give us a title, tension in string 3. So let's find the tension in string 3. And like I said, we're looking at just the single mass of 4.0 kilograms. And we draw the ground. And the forces, again, just like our last unit here. The forces, we have F tension, which we do not know the value of. We have an Fg, so our gravity, which is m times g, so 4.0 kilograms times 9.81 meters per second squared. And the value that Fg is equal to 39.24 newtons. And then the opposite of the gravity, going upwards, is going to be the normal force. That is equal and opposite magnitude to the force of gravity. So our Fn is just the same, but in the opposite direction, 39.24 newtons. Let me redraw this box. Okay. And then the force of friction. Force of friction is equal to mu times the normal force. So again, our mu, which was given in the question, 0.3 times 39.24 newtons. So that tells us that the force of friction is equal to 12.95 newtons. And this step here is going to be exactly the same as our last one, where we're going to write out our F net equals ma equation. And we know m, we know a, and then our F net, we just have a single unknown. So again, our F tension, that's in the positive direction. So F tension minus 12.95 newtons minus 12.95 newtons is equal to our mass. Let's look at our mass is 4 kilograms. Looking at just this last box. Mass is equal to 4.0 kilograms. And our acceleration, which is the same number as we used in this last step, which is the value that we got over here, 2.15 meters per second squared. Now all we have to do is isolate F tension. So it's equal to 4.0 kilograms times 2.15 meters per second squared. And this term here is coming to the other side, and it's going to change from a subtraction to an addition. So watch this. We go plus 12.95 newtons. And then all we have to do is add these up. First, I'm just going to multiply these two together. Get 8.6 newtons plus 12.95 newtons. And that gives us Ft is equal to 21.55 newtons. So F tension is equal to, and I'm going to round this just to 22, equal to 22 newtons in the third string. All right, so let's add these values to our table here. So 38 newtons in the second string, 38 newtons in the second string, and 22 newtons in the third string. 22 newtons in the third string. And I want to write these out here as well. So remember, tension is equal to 70 newtons. Tension was equal to 38 newtons. And tension is equal to 22 newtons. And it's interesting to note, and this will always be the case, and you'll know that you're on the right track and you'll be able to check that your answer makes sense, is that the tension, as you go from the first to the second to the third, it decreases with every string. So the first string has the highest tension, then the second, and then your last string will have the lowest tension. But that is all to this problem. Hope you guys were able to follow along well, and that is all for this example.